Record. Okay, I just started recording. Hello, good morning, good afternoon, everybody. Today we will attempt to prove at least halfway the theorem I announced before. But before we do that, I want to prove a lemma I was alluring to before, which we only needed for some corollary, and I skipped it because I thought it was too obvious, but I think it's a mistake. And I want to do it because we really use it at many places. Okay, so before we go to the proof of the theorem that I announced last time, let me prove this lemma. Okay, so everything happens in the absolute conpath algebra. So X is empty, E is any graph, and K is any field. So I'm making no assumptions here. Then, for any pair of regular vertices in E.
I'm sorry, maybe it's only
Yes?
me, but I
We
don't
don't
see
see.
any notes. Yes.
Oh, thank you so much. I'm afraid what I did is that I stopped, that I forgot to start sharing. This might be because, but it's strange because this is strange because it's visible here. So how come this is, no, I am sharing.
Wasn't it the same problem?
Yeah, we had this problem before. So that's Zoom. This is not my fault because I am sharing and we see it on screen in the lecture room. Okay. So thank you for telling me, but it's really the Zoom fault or a Zoom fault. Okay, share screen and whiteboard. Maybe the trick is that I have to start recording first and sharing next. Maybe these two operations do not commute. So if you start recording, you automatically stop sharing because somehow the Zoom is afraid that you are sharing unwillingly. So that's my only conjecture for the time being. Okay, can you see it now? Hello?
Yes.
Yes? I don't hear it. Can you see it now?
Yes, now we can see.
Good. Yes, I think that's the cause. All right, non-commutativity, you see it's everywhere in life. Okay, so we take a pair of regular vertices in our graph E, and we look at the absolute conpath algebra of E. And in this algebra, we have the following equality. So this holds, of course, for any such a pair. Is that in fact, when you look at these QVs and QWs, I have to write the equivalence classes because remember QV and QW were defined in the path algebra of extended graph. Then this is in the conpath algebra. So we divide by one relation. And I claim that this family labeled by regular vertices of these QVs is a family of mutually orthogonal idempotents. Okay? So this is equal to the Kroneker's delta of VW, and then of course the class of QV or QW, whatever you want. Okay. Also, as a byproduct, you can immediately conclude it once you prove this, is that when you look at the class of chi V itself, and you subtract QV, and again we are going to use it all the time in the proof of the theorem, then this is an idempotent. So this squared is equal to itself. Okay. So this is a very simple lemma, but I decided to prove it because we already needed it for a corollary I was arguing for in my previous lecture. And secondly, it's appearing in a significant way in the proof of a theorem, which we are doing today. Okay, so this is just a simple calculation. Let me do it. I just take this multiplication and compute. All right, I plug in the definition and I see what I get. So I'm just multiplying chi V minus sum over E running the preimage of the source map of V. This is regular vertex, so this is a final sum. And I have classes of chi E, classes of chi E star, And I'm doing basically exactly the same, but now with a W instead of V, okay? So class of chi W less sum. Now let's choose the dummy variable to be F, running the preimage of W under S, the class of chi F times the class of chi F star. Okay. So now we really multiply it out. And you see one of the things that you can see immediately, so that we abbreviate the notation a little bit. When QV meets QW, of course, we have Kroneker's delta. That's just in the path algebra. Now, if you look at the beginning of the edge E, this is exactly V. So I might as well write here in front of everything chi V, the class of chi V. Now, the end of E star is the beginning of E. So again, I can write at the back here chi V, all right? And the same with chi W. So if you want, I can sandwich what is in parentheses between chi V for the left term and chi W for the right term. So now it's obvious that when we multiply, we always have this chi V meeting chi W, so Kroneker's delta is unavoidable, okay? So I can just write Kroneker's delta and then write everything else with V equal to W, okay? So this is the first simplification. And then of course, it becomes nothing else but the class of chi V minus the sum over E is running the preimage of V under S, chi E star squared, okay? And now we just compute what this square is, and this is very easy. We'll just, multiply everything out and see what we get and how it beautifully simplifies. So for starters, of course, we have everywhere. So we have this big delta VW and a big parenthesis. And of course, first you have the class of chi V squared. Then you subtract and you have the sum, the same dummy variable as before. And now here you have chi V, chi E star. When you subtract it again, but this time you have this chi V on the other side. So it's chi E star chi V. And you have the last term, which is the square of the sum, okay? So now we have to do the following. We have to choose another dummy variable because it's a double summation. So now it's the sum over EF running the preimage of V under S. And now what we have, I'll try to squeeze it in, is chi E star, chi F star. And you see, this is the only place when I'm actually using what is in the conpath algebra. Here, I need the Kroneker's delta between E and F. Everything else is actually in the path algebra of extended graph. That's the only place where I need this extra relation. And I have this extra relation, then you can easily see what happens. So for starters, this is an idempotent. So this is just the class of chi V. Okay. And now V is the beginning of V, so I can just ignore it. It's absorbed into chi E. Again, V is the end of E star, so I can just ignore it. It's absorbed. And now when you look at this one, because you get this Kroneker's delta EF, this double summation becomes single summation with E equal to F. And when you have single summation and E is equal to F, well, then chi E star chi E will give you chi of the end of E, right? But chi E times chi of the end of E will be just chi E, so it will be absorbed. So I can just cross it out, okay? And I end up with the same sum. So I subtract this sum twice, I added once. So I subtracted once, okay? So let me write the result on the next page. So the result will be just the class of chi V. Sorry, there's this big Kroneker's delta, I'll write it at the end. Minus sum over E running the preimage of V under S. The class of chi E, oops, the same mistake, I shouldn't write too high. The class of chi E star, and this is times Kroneker's delta. VW. Okay, so this proves to us the first equality. And now the second equality easily follows, because in particular we proved that QV is an idempotent. Okay, and now remember, if QV is idempotent, well, now we easily have when I compute chi v minus q v squared. Well, chi v is an idempotent, q v is an idempotent. All right, and then when you look at cross terms, it's immediate that chi v times q v is q v, and q v times chi v is again q v. Chi v is just absorbed into q v. Okay, so when you remember this, you will immediately get that this is chi v, and you have twice minus qv minus qv, and you have 1 times plus qv. So that's exactly what you wanted, which is plus the class of chi v minus once the class of qv. So it is also not important. So this is just a simple technical lemma. Actually, it's not just technical, because it's conceptually important that these elements in the concav algebra that we are putting to 0, namely these QVs, right? Because when if V is in X and we have a relative concav algebra with respect to X, then the class of QV when V is in X is 0, right? So what we are killing is idempotence. And this is very important in the study of Levi-Pav algebras, because you have very, very strong structural theorems telling you that ideals for natural algebra homomorphisms, for instance, equivariant, or if you want preserving the grading, must be always generated by idempotence, given by vertices. So this is amazing. This is a very strong structural theorem for ideals for kernels of your maps. And then you can prove some other important theorems using structural knowledge about the ideals. Okay, so that's not just technical; it's actually also conceptually important. Okay, so now with this lemma proven, now the corollary that we discussed, if you remember the corollary about what it is when I take QV times the concav algebra CKE, the whole algebra, and here I take QW, that this is equal to the Kronecker delta and the class of QW, well, times the ground field K, right? So from the previous lemma, we see that everything cancels out except when this is a vertex. But then what we were lacking in this calculation is the knowledge that these QVs are mutually orthogonal idempotents. And this is what we just proved. Okay, so now this corollary easily follows. Okay, so now we can start working on our theorem. And I announced this theorem in a very simple form, that there is an isomorphism between the concav algebra and the Levi-Pav algebra for appropriate graphs. But what is very important actually is how you implement this isomorphism. And I apologize in advance. It's the theorem in itself is unexpected. And I find it spectacular because this is a very strong and completely general result. And because it's unexpected, I truly appreciate it. And it's also conceptually important and technically useful. But the proof itself, although not as boring as the proof of a basis theorem, right? Where you have to prove a basis theorem in almost every example we touch, and there are some standard techniques to do it. So the previous main theorem was really horrible. This one is not that horrible. There are two relatively interesting calculations, but again, I have to warn in advance that much of it is just extremely tedious checking of zillions of cases. Okay, there is no trick, no nothing. There are just two calculations which are somewhat more interesting, and I'm going to highlight them. They are also tucked into the lecture notes, but the rest is just checking the cases, okay? So here, if you want the whole proof, it's just plug and play. There is no trick. So the only trick is to invent this isomorphism, to see what your formula should be. Once you write your formula, proving that it's well-defined and that these are mutually inverse formulas is plug and play. At some places it's trivial, at some places it requires some calculations, but it's plug and play. All right, so now let me very, very carefully write the statement of this theorem. And the statement is going to be very long because I'm going to give these lengthy recipes for both psi and psi inverse, okay? So that's our theorem of the day. Let E be a graph. X be a subset in the set of regular vertices of E. We define Y, this is important, as the complement of X in the set of regular vertices. So it's regular vertices less X. Okay. And K be a field. Okay, then the formula and now comes this horrible looking formula. And please remember that this is just the general case of what Maciek did at the recitation class a week ago. So we're working just with a simple graph E, which was transformed into the extended graph like this, okay? And even in this case, Maciek took like half an hour to prove it, okay? That these are isomorphic algebras. So it does require some work. It's not immediate, but as I told you, most of it is boring, tedious checking. However, there are some calculations which are a little bit more fun. Okay, so then the formula, and now I have to write it very carefully. It's 2 pages just to phrase the theorem. So I start with my relative x-relative con path algebra of my graph E over a field K. I take the equivalence class, and here it's very important. I abuse the notation in the following way. I'm using the same symbol for the equivalence class, whether it is in the relative con path algebra or in the Levi path algebra of another graph. I use the same. If I were very pedantic, I should decorate these brackets, okay? But it's too much. I'm already using very Baroque notation. Many people would ignore the sky and so on and so forth, but I insist on keeping it because I insist on distinguishing this natural semi-ring of finite paths that we have from really path algebra, because one thing involves a field and the other one doesn't. And I somehow want to keep it distinct. Okay, so we view it as the universal algebra given by generators and relations. Okay, so I'm just looking at the generators. What are the generators? These are vertices, these are edges, and these are ghost edges. That's it. Everything else in the path algebra of extended graph is generated by multiplication. Okay, and then you just divide it first by relations that define your path algebra, and then by relations that define your relative compact algebra. So in fact, we will have later on 5 relations to check. But first, let's see what it is from generators. And it's not so easy to write it down. I need this huge brace. And for starters, when P is a vertex in Y, so it's a regular vertex which is not in X, so it's a vertex at which we do not implement the second Kunst-Krüger relation, then, surprise, surprise, we double it. So it's the chi of P plus the chi of P prime. Okay? So P prime is not in E, but it is in EX. So this chi P and this chi P are different animals, all right? But it's obvious from the context, so I'm not going to label it in some other way. Okay, now if I have P, which is in E0, but not in Y, then I do nothing. So this includes regular vertices and irregular vertices, okay? Although I haven't met anybody saying irregular vertex. I mean a vertex which is not regular. I remember once Bornov was objecting to calling operators that are not normal, abnormal operators. No, don't say it. They're not abnormal operators. Okay. Now, we have, and that's it, right? That's it, because we have nothing more. E0 is split into two disjoint sets, and we have a recipe. Now, what happens with the edges? So we can have P, which is, well, let me write okay, I can write that P is not here, but let me write that P is in E1, but I'll write it very explicitly. And its end is in Y. So we call such edges elements of F, if you remember. So I could just write for P in F, okay? But I wrote it explicitly. And then again, we double it, yeah? So we have a class of P plus the class of P prime. So, but here P and P prime are oops, I forgot chi. Here P and P prime are vertices, and here P and P prime are edges. But because P is an edge which ends in Y, it's also double. Okay, and as you can guess, otherwise, so for P, which has the property that it does not end in Y, okay, then we do nothing. And finally, we have to say what happens to the stars. Well, this is completely analogous. So again, if I take now P equal to E star, sorry, I wanted equal. Equal to E star, where E is an edge, and let me write it down that this is E is an edge in F, okay? So this means that the end of E is in Y, okay? So then what we do, we double again. So we write chi P, but this chi P is now chi E star. And you can wonder why I did this Baroque notation, because right now I have to add chi E prime star. Okay, otherwise it wouldn't make sense. So I never told you what it is, E prime star. Okay, so I cannot just take E star and prime it. But what I can do, I can take E prime and star, right? Although, I mean, you could just define it like this. So whichever way, it's if you really look carefully at the extended graph of EX, then you'll have such elements. Okay, but this is sort of for me more primordial. So I know that if E ends in Y, then I also get prime, and then I can star both of them. Okay, I'm not claiming that this is the best possible notation. So it's a bit ugly because I use E and P simultaneously, so it's a bit confusing. Okay, but it's obvious what I mean. And then, of course, when you have E which is not in F, so again for P equal to E star, but this time E not in F, I have simply chi of E star. Okay. Yeah, it could have been written in a better way, but let's leave it like this. There is no point of pondering about trivialities. So what's the end of a sentence? So then the formula, this beastly formula with 3 lines, defines an isomorphism psi, which goes from the relative conv algebra, the X relative conv algebra, to the Leavitt-Pav algebra of the graph EX, an isomorphism of algebras. Okay, and I want explicitly also to state its inverse. So its inverse is given by the formula. And again, what we use, we write this Leavitt-Pav algebra of EX in terms of generators and relations. So we treat it as the universal algebra given by generators and relations. And again, we only have to say what happens at vertices of EX and what happens at edges of EX and at the edges start of EX. Okay. So that's quite a lengthy formula. This time I have 9 cases. Okay, so it was 6, now it's 9. And that's because here we have more generators because we added these primed things. Okay. But you have to write this formula anyway to do the verification. So instead of scattering it all over the proof, I think it's far more beneficial to have it in the claim of a theorem. Because the theorem doesn't just say that these algebras are isomorphic. They say that an isomorphism is implemented by such and such maps. And that's actually important to do calculations. Okay. So now I take chi p. So this is in the Leavitt-Pav algebra. And I have to squeeze it in. Again, I have a gigantic brace. But now I'll have to write with smaller fonts to squeeze in 9 lines because I wouldn't like to break it. Okay, so for starters, yeah, but you see here I really have to do it because I have this operation of depriming. Again, I could have defined some operation on vertices and so on and so forth and avoid such clumsy notation, but it would be at the price of introducing even more notation. So let's not dwell on trivialities, just do it. So when I have P, which is equal to V prime, and V is in Y. So in other words, V prime is in Y prime. So I could write for P in Y prime, but then I have to deprime the P. So I have to write it down as P of V prime. And then it's just a class of QV. Okay. Next. What happens when P is in Y? I don't need to deprime, so I can just write P in Y. Well, something interesting happens. Namely, we get the class of chi P less the class of QP. And you see, it makes sense. So remember that we are in the right-hand side, the right-hand side of psi inverse, which is the left-hand side of psi. So we are in the X relative concav algebra. And you see, if P were in X, this would be 0 because we have a second conjugate relation, which means exactly that QP vanishes. All right. But because P is in Y, that's exactly where we do not implement the second conjugate relation. So this term is important. It doesn't vanish. Okay. All right. And now when I take P in E0 less Y. So again, I split my set of vertices into 3 disjoint subsets. I have my Y prime vertices, I have my Y vertices, so the vertices which I double to Y prime, and I have all other vertices, not only regular. Okay. So here for a second, I thought that maybe writing this is redundant because the second line becomes the third line for P in X. But we might have also vertices which are neither in X nor in Y. Okay, so as I said, irregular vertices. Then you use this formula, which means you do nothing. I don't see how I can squeeze 9 lines. Okay, I'm trying, but it's hard. So now we look at the edges, all right? And I take P, which is in F. Sorry, no. I take P, which is in F prime, if you want. Okay, so P is equal to E prime, and E is in F. Okay, so well, something funny happens here. I have to deprime the P, so I take the class of chi E. Okay, And when I take multiply it by the q taken at the vertex, which is the endpoint of E. So here I have to write this TEX, because remember, this is the right-hand side. So I'm now landing, wait a second. No, this is T. Okay, so the image of psi inverse is the relative con. Okay, so I don't so I see I made errors in what I wrote. This is not EX, this is just E. This is just E because here we are on the right-hand side of psi inverse, and the right-hand side of psi inverse, the left-hand side of psi, which is the relative con of algebra. So this is just TE. I have just a graph E, not EX. Okay, so this simplifies the notation. Okay, so this is what we have. Now it gets even more fun if P is in F. So this is if you want P in F prime, but I wrote it as E prime in order for D prime. So for P in F, well, then I get the class of chi P. Now I have to D prime it, so I just write it. But here, lo and behold, I multiply by something complicated, is the class of chi TE of P minus the class of Q TE of P. Wow, I mean, I really should make clear what I mean. Okay, and close parentheses. Okay, and so this is what happens for things in F prime, for things in F, but how about all other edges? Okay, so if you want, I'm looking at edges which are in E1, but less F. Okay, so they simply don't end, they're edges in E1 and they don't end in F. Okay. They don't belong to F, so they don't end in Y. Sorry, this is where to put it. Then we do nothing. So as usual, things get simple when you avoid dy. When you avoid y and y prime, when you avoid f and f prime, things are simple. Nothing changes. This is like the tautological part of these maps, psi prime. Okay, so I managed to squeeze 6, and I'm afraid I have to write C the next page. I apologize for this. But I cannot use any smaller fonts. So we continue this formula. We have 3 more lines. Now I have to say what happens for the stars. Okay, so I'm taking P equal to E prime star, and of course E is in F, so that I can double it. Okay, then what we expect should happen. Remember that this star is an involution to B. An involution is an anti-algebra homomorphism. So I should take the formula for E prime and apply the involution. So look what happens here. That's 1, 2, 3. This is what we are talking about. But now we start. Okay. So when I start this formula here, I reverse the order. So I write QTE first. That's if you want self-adjoint. This is a projection. This is self-adjoint. Right? So you don't star it, and then you start chi E, which is chi star. Okay. So and this is actually the formula. So it's the class of Q TE of E times the class of chi E star. And here I really had to write it like this because again I am depriming it. And here I'm depriming and destarring it. So it's really useful to write it like this. Okay, and exactly the same principle holds for the other 2 formulas. I apply the star to this expression, so I flip it to the left hand side. So then I'll have chi P star here. I'll have appropriate things over there, and this is what gives me the formula. Okay. So now it's for P equal to E star and E again in F. Okay, so if you want, this was P was in F prime and now P is in F. So now you write this complicated formula. Oops, I really have to squeeze it in. So this is the class of the chi of TE of E minus class of Q at the same vertex, which is TE of E. So that's the self-adjoint part if you want. And now we multiply it by the class of chi E star. Okay. And finally, nothing happens when I have for P equal to E star and E not in F. I mean, to be more precise, E belongs to E1 less F. This is a better way to write it. Yes, this is a better way to write. Then we do nothing. It's chi E star, right? So this ends the formula. I have these nine things. I can now begin proving the theorem. And the strategy of the proof is very simple. For both psi and psi inverse, we're going to prove that they are well-defined algebra homomorphisms, which we can do because we present these algebras as universal algebras given by general set relations, and proving that they are such is very easy. I will delegate it to some recitation class. It's really straightforward. It's a straightforward exercise, so let's take it for granted right now, not to muddy the waters. And we will just have to prove that these formulas, which are spelled out for you, preserve the relations. That's it. This is our only job. Okay, well, almost. Then we'll still have to prove that these guys are mutually inverse to each other, which again is a calculation. I mean, there's nothing difficult, but you have to compute it. It's not like you can do it in your memory. Okay, and this will definitely not manage to do today. Remember that there are so many cases when I have some pair and I have 9 cases here, 9 cases there, it's like 81. So I'm not going to do everything, but I think it's important to have everything checked. And except for this psi being really the inverse of psi inverse, I checked all formulas. It took me like 6 pages of paper, but it works. Okay, but it's very important to state of what explicitly are the conditions to be satisfied so that you can say, aha, so psi is a well-defined star, it's a well-defined algebra homomorphism. Okay. So for starters, viewing the relative compact algebra, this is X, CKXE as the universal algebra given by generators and relations, we easily verify that the above formula defines an algebra homomorphism. And this easily verify means that we have to check 5 conditions. And this is what I'm going to spell out for you. So first, for any pair of vertices in E, we must have, so these are path algebraic relations to begin with, but these are mutually orthogonal idempotents, okay? So we must have a psi of chi V chi W. It must be, it must be the same as psi of a conic cross delta VW times the class of chi V. Okay. So that's the first axiom in the definition of a path algebra, the path algebra of a graph, of the extended graph of E. Okay, now the second one concerns edges. So now we take any edge E in E1, and we must have that if I take the beginning of this edge and I multiply it by the edge, I do nothing. I just get the edge. So the class of psi of SE times the class of, chi of SE times the class of chi of E itself, okay? This is supposed to be the same as psi of the class of chi E. And we do the same with the end. So this is psi of the class of chi E times the class of chi of the end of E. Yes. And here I should have been more pedantic. This is in the graph E. This is SE. This is TE. Well, you can say that this is, so the domain of psi is this relative con path algebra. Yeah, so we are in the graph E. This is correct. And now we have to say what happens for the starred edges. So I still take E in E1, but now I will star it. And you only have to remember that the beginning of E star is the end of E, and the end of E star is the beginning of E. So you have completely analogous formulas to verify. Now I write chi TE of E. And here I write chi E star. Now I have again chi of E star. And now the same, but with chi E replaced by chi E star and chi TE replaced by chi SE. So if I just check these three conditions, now I say, aha, so I have a well-defined algebra homomorphism from the path algebra of the extended graph of E. Okay, that's it. But this is the relative compact algebra. So I have two more conditions to satisfy. First conspicuous relations and second conspicuous relations. So now the fun begins. And actually only the second conspicuous relation is fun. It's the only one where you have some calculation, not just checking cases. Okay, so let me write it down. This first conspicuous relation. So now for any pair of edges in E1, we must have that psi of chi F star times chi E. It must be the same as psi of the Kronecker delta of E and F times chi at the vertex, which is the end of E or F, whatever, they are the same. So that's the first conspicuous relation. And now the most important one. That's actually the name of the game here. Now we say that for any vertex in X, okay, so the regular vertex which is in X in our subset, the following is true. If I take psi of the sum over all edges in the all edges emitted at V. Okay, that's the way to put it nicely. And you have chi E star. Okay, then this must be the same as psi of chi of V. Because here we do implement this second conspicuous relation, so it must be preserved by psi. And that's what we have to verify. Okay, so the first four conditions are straightforward to check. So I will start by proving the fifth one, and then time permitting, we still have 45 minutes. I will see how much verifications we can do for the first 4 of them. Okay, at least some center. You see, once you do 3, doing 4 is completely analogous. Sorry. Once you do 2, doing 3 is completely analogous. That would be just a waste of time. But I mean, these are, of course, just tedious checking, but they still teach you something. You have some insight as to how all this works. But let's begin with the interesting part. So checking number 5. And condition 5 follows from the following calculation. Okay. If I take E, which is in F, okay, so it has this double in F prime. So if I take the class of chi of E, and I add to it the class of chi E prime, maybe I'll write for E, I'm doing it for E in F, okay, so that the doubles exist. And now I multiply, but the same thing, but start. So the class of chi E star plus the class of chi E prime star. I'll just need to figure out what it is. Okay. All right. So we just do it. We have obviously 4 terms. We'll have chi E star. So these are the terms which we like and want to keep. Likewise, we have nothing against the terms chi E prime star. That's what we like. But we have these ugly cross terms, which we want to get rid of. And let's see how we do it. So first, we will have, say, chi E prime times chi E star. But of course, nobody can stop me from writing chi E prime as chi E prime times chi with the end of E prime. But what is the end of E prime? It's the end of E prime. Okay. And likewise, nobody can stop me from writing chi E star as chi of S of E star chi E star. All right. But what is the beginning of E star? It's the end of E. So it's times the class of chi TE of E, and then chi E star. Okay. In the same fashion, now I have chi E and chi E prime star. Again, I use exactly the same trick if you want. So I have chi E times chi T of E and here I'll have to look at the beginning. I have to look at the beginning of E prime star. So sorry, yes, the beginning of E prime star is the end of E prime, but the end of E prime is the end of E prime. And times the class of chi E prime star. Okay, and now we are home and dry because you see, by construction, TE, or maybe let me write it and then it will be nicer. So just these two cross terms disappear, and we have what we wanted, notably chi E star plus chi E prime star. And this is because for any E, TE of E is always different from TE of E prime. Remember, we said that Y prime is a set, is a disjoint copy of vertices in Y. So it's by construction. These are disjoint subsets. Okay, so then of course when you multiply two vertices which are different, it's zero by properties of the path algebra itself. Okay, so this is a very nice calculation. I mean, of course it's trivial, but at least here you really dig into the inner workings of the construction. You really use how it was set up. Okay, and now you can easily check the condition number 5, right? So what is the condition number 5? We just have to do this calculation, but in order to do this calculation, of course, we have to see what happens to psi applied to chi-e and chi-e star. And here, this is why it gets so tedious and complicated, because we have our assumptions about v, but v is the beginning of e. An edge emitted from v can end anywhere. There's no restriction on ending. And then, depending on when we, or on where these edges end, we write such and no other formulas. Okay, so let's do this calculation. I have no choice. I just compute. I write this psi. Okay, so this is psi of that sum of make sure. Okay, so it's chi-e star. Okay, let's make sure I'm consistent with notation. Well, first step is completely obvious. It's actually almost embarrassing to write it down. Of course, put psi inside. That is how it is defined here. It's like construction. And now we have to check cases. So for the time being, let me skip all these notations. I will just stop writing equivalence classes. I'll stop writing chi's because it just clutters the view. Now we understand conceptually what we are talking about, and we have to see what happens. All right. So the formula for psi depends on where e ends. Okay. So in other words, we can say that here, either this e is in F or it is not in F. Okay, it's in the relative compact algebra, so there are no primed edges. Okay, so we don't have to check this one. It will be more complicated the other way around. So we have sort of 3 cases. Because you see, it's the first time it's 2 times 3. Because we always have to have vertices, edges, and starred edges. But for psi, we just either take y or not in y, or we take f or not in f. That's it. But when we are on the other side, in the Levitt algebra, we have y prime, we have y, and in E0 not in y, and the same with edges. So it's 3 times 3 for the other side. Okay. So now let me do it informally. By skipping this Baroque notation, and let's see what happens in the first case when E is in F. Where E is in F, let's see what psi does to it. You have to backtrack quite a bit. So that's the case when E is in F, I presume. Yes, that's here. P is in E1 and ends in Y. So this is when we have to double. All right. This is when we have to double. So what psi does, it will give us E. Okay, I'll have a sum. Oops. I'll have a sum over, well, here, okay. I take it back. I'm now looking at particular sums. All right. So if you want, I split the sum into two sums. Into one bag, I put edges that are in F, and then to the other bag, I put edges which are not in F. Okay. So this sum, well, maybe I can still, before I go to checking the cases. Eraser. Let me write it in the following fashion. I will not write the summands, but I'll say what happens with the range of the summation. So I'll have a sum, because the summands will be identical. So I'll put just 3 dots. I'll have E, which belongs to SE, the preimage of V, but intersected with F, okay? And plus the complementing sum, where I have E emitted at V, but intersected with E1 minus F. Okay, so these are which are not in F. And the same sum, because we have now different formulas for these edges, okay? And we just established that when these edges are in F, we do the doubling, right? That's the recipe we looked at here, this one. When an edge is in F, we do the doubling. But when we do the doubling, you see what happens. I have this E plus E prime, and then I have E star, because you see the formulas for star are analogous. So I'm just starring it. Let me not go and double check. Just that's the way it is. And this is why we use this formula. So now because we know what it is, look what happens for the first sum here. We will have things which are in F plus things which are in F prime, because all these cross terms will cancel, yeah, on after applying. So here still psi lingers on, but when we want to get rid of psi, the first sum will split into two sums. Okay. Okay. So the sum it will be the sum over E in F, and now this is a different. I promise not to write this for this class. Okay, so I'll write just E star and plus the sum of E in F prime and E star. Okay, that's what we got from the first sum. And now when you look at the second summand, or maybe let's redown it. Let me erase it. I can view it as a more informal written calculation of what we had before. Now I'm going to the third summand, I mean the second summand, which will now become a third, and these are guys which are not in F. Okay, and when we are not in F, we double check the formula. When we are not in F, which is this case here, we do nothing. So this will be just FF star or E star. Okay. So plus the sum, and now we run over E, which are in E1 less F. Okay, and this is again E star. But when you look at it, then of course what you will get the sum of E stars, but now E really runs the pre-image of EX under EX of a vertex V. Again, well, one should be a little bit careful, because we have to still see what happens at No, actually, no, this is correct. What I said is correct. Yeah, that's this is exactly that sum that we obtained over here. And this is a result of computing the left-hand side of a condition 5. Okay. Right. And now we have to look at the right-hand side. And the right-hand side is just psi of chi v. And now we have to use what actually it is, what psi does to chi v when v is in x. Well, but that's easy, I suppose. So now we are looking at the vertex. And when your vertex is not in y, so in particular, if it is in x, is not in y, we do nothing, which is good. Which is good because remember that this is now in the Leavitt path algebra of Ex. So this is equal to V. But then this is equal exactly to psi of V. Okay. So that's a lot of writing, but it's not so. We have to consider some cases. All right, so this way we proved the condition number 5. And let's see how we can check other conditions. Say, I'm definitely not going to check 4 because it's very much like 3. So let's, sorry, I'm not going to, sorry, 4 is actually different. 4 is interesting. Well, I take it back. It's not interesting, but I guess it's slightly more involved than say 1, and it doesn't follow from anything else. So what I want to skip is 3. Let's see how we verify 4. All right. Okay, so now we have to do some cases because we have EF running E1, so we'll have 4 cases. So verifying 4 cases. We have E and F, right? And either we are in F or we are in E1 less F, okay? And these cases are, it's actually nice to have different notation. So let's call this F and call this G. So this will be for the left-hand side. And here, let's call this E and let's call this H. Okay, so F is in F, E is in F, G is not in F, and H is not in F. Okay, and now we will have to compute this formula in 4 cases. All right, so let's do it again. I'm skipping all these equivalence classes and chi's. So first, let's take F and E. Well, where do we map it? Where F is in F and E is in F, then our psi does the doubling, right? Let's double check. Yes, when we are in F, we do the doubling. But this is a calculation all it did, right? Almost. Okay. So we have F prime, sorry, we have F star plus F prime star times E plus E prime, okay? That's what we have to compute. Well, the first term is F star E. That's a good sign. The second term is F prime star E prime. And then we have these cross terms. So let's say F star E prime and F prime star E. Okay, so what happens over here? The Kroneker's delta between E and F is the same as Kroneker's delta between E prime and F prime, because this is a bijective correspondence between F and F prime. Okay, And now let's see what happens here. The edge f and d prime cannot be the same ever, even if f is equal to e, then still e is not the same as e prime, okay? Because f does not end in y prime and e prime ends in y prime. So they are definitely different edges. By the same token, f prime cannot be equal to e. Okay, so this is just zero immediately. So cross term vanish. Okay, remember this is in the Levitt path algebra of Ex, and these have different ends. So already, for the sake of having the path algebra of Ex, they have to die. And now here we have the same Kroneker's delta. So I can write delta EF because, as I said, delta EF is the same as delta E prime F prime. Okay, and then what? If E is equal to F, then we simply have E star E, but that's, we are in the Levitt path algebra, so this is the same as the end in this graph EX of E, but E is in F, so this is in the subgraph E, so I can just write TE of E. Okay, and the other one, well, it's exactly the same because I have now E prime star E prime, so this is the end of E prime, but the end of E prime is the end of E prime. Okay, so this is what we get as the result of this formula in this case. Yeah, I hope I didn't make a mistake anywhere. And now, hopefully, this is really what we want to get. Because, yeah, and I think we do. Because if you look at the right-hand side, you should have Kroneker's delta. We have Kroneker's delta. This is just a number. I can pull it up. But now, remember, P is in F. So this means that T of E is in F, capital F. So its end is in Y. If its end is in Y, remember we double vertices. Oh, sorry, I went too far. You see, when your vertex is in Y, you double it. And here, because E is in F, its end is by definition in Y. So in other words, I can now write it down as delta EF psi of T EE. Okay, because psi will just double it, and this is the same as psi of delta EF. And here, of course, I can write F star E. Okay. So that's because, of course, this is the first configuration relation, and it works on the side of the compact algebra. I don't have to be in the Levitt to have it in the first. And I'm always curious if I screw up this T. Well, I mean, here to be completely formal at the side of the Levitt path algebra, I should write EX, but because we're in the subgraph, then I can skip it. Okay. So for instance, I can write T E X of E prime is equal to T E of E prime. That's simplifies the notation a little bit and makes perfect sense. Okay, so you see, we checked the case number 4. We have 21 minutes. All right, let's see. We skip number 3. Let's check number 2. Okay, let's check number 2. Skipping again the notation. So, okay, so this is with the beginning and the end. All right. So checking condition number 2. All right. So first, it will be easier to check at the ends. So what we want to check is that if I take psi of E times the end of E, okay, it will be the same as psi of E, psi of T of E. And well, let's see how many cases have we got here. Well, either E is in F or E is not in F. Luckily here we have just two cases, right? Obviously. So this one, of course, this is just psi of E. And if E is in F, so this is equal. If E is in F, then we double. So this is E plus E prime for E in F. And this is just E if E is not in F. Okay, so this is what we have here. Now, so again, here we have this the same two cases, E plus E prime and E, or E in F and E not in F. And now we multiply it by psi of T. But you see, if E is in F, then TE is in Y. Okay, so I multiplied by TE plus TE prime. So it's time, oops. So it's times, sorry, I just erase it. So here I write TE plus TE prime. Okay, this is for E in F. Well, when E is not in F, then its end is not in Y, so we don't double it. So I just write E times T of E. Okay. So of course, now what we obtain down below is obvious. It's just E for E not in F, and this agrees with this line. But here it's a bit more interesting because we have four terms, right? But again, we use this argument that we did before, that the end of E prime, which is the end of E prime by definition, cannot be the same as the end of E. So E prime times T of E is 0, and E times TE prime must be 0. So cross term vanish, okay? And then we have just ETE and E prime TE prime, okay? And this is obviously just E plus E prime, which agrees with the previous formula, okay? So 2 is checked, and 3 is completely analogous. So we have one last condition to verify with this orthogonality of idempotents given by vertices. Okay, so checking 1. And here we will have 4 cases. We will have, say, V and U, depending on whether we are in Y or we are not in Y. And here we'll have W and say whatever, Z, okay? All right, so first let's do psi of V times psi of W. Now we are in Y, so we double them. So this will be equal to V plus V prime times W plus W prime. But these are all in the Levitt algebra of the graph EX. So these are mutually orthogonal idempotents. So it's obvious what we are going to get, remembering that Kroneker's delta of V and W is the same as Kroneker's delta of V prime and W prime. We'll explain this. We will get obviously the two terms as we want with the correct Kroneker's delta. But you also have to look at the cross terms, but they have to be annihilated because V prime can never be W and W prime can never be V in disjoint subsets. Okay, so we obviously end up with the Kroneker's delta VW, and then, well, we have V prime W prime and VW, but now V is equal to W, so we have V squared and V prime squared, but they are idempotents. So this is V plus V prime. Okay. But now this is exactly what we want, because if I compute psi of VW, this is Kroneker's delta psi of V, but V is in Y. Okay. So this is, well, it's exactly this. Okay. So first out of 4 cases is checked. Now let's do V and Z. Okay, so psi of V times psi of Z. Well, we'll have V plus V prime. And now we multiply simply by Z because Z is not in Y, so we don't know. Okay, so V prime times Z is obviously 0 because they are different vertices. So we are left with the Kroneker's delta of V and Z. V times Z. That's sorry, V, yeah, V squared, which is V. Okay, but this is uh-oh, wait a second. Wait a second. No, I think this is immediately 0 because you see Z is not in Y and V is in Y. So V prime is in Y prime, V is in Y, and Z is not in Y prime and not in Y. So this is just 0. No Kroneker's delta. This is just 0. Okay. As it should be, because now if I write psi of VZ, V and Z are from different sets. So this will be 0. So 0 equals to 0. Done. So now U and V. Psi of U times psi. Sorry, not V, W. But this will be exactly the same reasoning because now psi of U is just U. We change nothing, and here we have to write W plus W prime. But again, W is in Y, W prime is in Y prime, U is beyond these two sets, so that's 0. So we have just the last condition when we have what? This was U and Z. So psi of U times psi of Z. Now they are both in E0 or less Y, okay? And well, so that is just U times Z. So that's really as we want. Kroneker's delta between U and Z, U. And now of course, this is what we want, because if I multiply on the con side, U times Z, again, it will give me Kroneker's delta between U and Z. And U, but now U is not in U is not in Y, okay? So we do nothing, and the formula is. So I think we verified everything. Because this was already checking number 1. Yes, yeah. So summarizing. Psi is a well-defined summarizing. Psi is a well-defined algebra homomorphism. Okay, and now we move on to psi inverse. To prove that it is well defined, we need to check analogous 5 conditions. One. So for any pair of vertices, VW, and to make it simpler, I write, instead of writing EX0, I already remember what it is. So this is E0, disjoint union with Y prime. This immediately will give you cases to consider. And now we have to show that psi inverse of the class of chi V times the class of chi W is equal to psi inverse Kroneker's delta between V and W times the class of chi V or chi W, whatever. Okay, so these are the same relations, but now you see our set of so our set of vertices is different. Remember that vertices in Y are doubled, so we have a bit more work to do. Now, the second path theoretic relation. So we take all edges in EX1, but this means edges in E1, and then edges that we double, and we double the edges of F. So this is disjoint union with F prime. That's a bit confusing. This is 1 and this is prime. In LaTeX it works. In my handwriting, not really. Okay, and we write psi inverse of chi, and here we have to write this carefully because you see we have to use EX because E is an edge in EX, not in E. So here I have to write this Baroque SEX. This is horrible. I have chi subscript S, S subscript E, E subscript X. That's just horrible. I'm sorry about this stairway to heaven. Not to mention what it reads. Pun not intended. Okay, so this that's not the way I should write it. Because it's SEX applied to E, not chi applied to E. And to make it even more fun, of course, I have to take the class. But now it's just the class of chi E. All right, it must be the same as psi inverse just of chi E. And it must be the same as, and now I write psi inverse of, but now chi E goes first. And here we have chi and we take the end, so tex, T-E-X, sorry, this is capital E, T-E-X of E, and that's it. Now the third condition is just the start version. So I take any E in EX1 and take its star. But again, I have to view it as something which is either in E1 or in F prime. So here the formulas are analogous, except that I have to interchange S with T because the end of the star is the beginning of the and blah, blah, blah. So let me write it down. So psi inverse of, and now it will be chi T E X of E times chi of E star. It's the same as psi inverse of the class of chi of E star. And this is the same as psi inverse. And now we first write the class of chi E star. And now the end of the star will be the beginning of E. So the class of chi of SEX of E. Okay. And the Kunz-Krieger conditions. They're actually easier to write down. It's completely analogous. But if you want, what really changes are the quantifiers. So for any EF in E1 union F prime, we must have a psi inverse of the class of chi f star times the class of chi e must be psi inverse over Kroneker's delta between E and F, the class of chi TEX, so the end of E. Well, and now we have the most important Kunz-Krüger relation, the second one. And now it's very important. We're in the Leavitt path algebra. So we must take all regular vertices in EX. But remember, some time ago, we proved that regular vertices in EX are the regular vertices in E. Okay, that's why I can write it down. So okay, I should really write it down for all V, which is a regular vertex in EX. But I know we discussed it, we proved it, that this is the same as a regular vertex in E. We must have it psi inverse of the sum over all edges emitted at V. So E belongs into SEX preimage of V. And you see here it's very important labeling the source and the target map, okay? Because V is simultaneously in E and in EX. So you can take preimage in the ambient graph or in the subgraph, and this is completely different story. Yeah, and that's very important to make this distinction. This really is used in calculations. It would be wrong without this label X, I think. So now we have, of course, chi E star. Well, and guess what? It must be equal to psi inverse applied I of B. Right? Because remember, this is in the Leavitt path algebra. So this equality always holds for every regular vertex. Okay, so we must verify for every regular vertex of EX, but luckily it's just the same as regular vertex of E. And now, of course, we will have to again split it into two cases because the V can be in X or in Y. And then this formula will give me something different. And this formula was quite complicated, if you remember. We have these 9 cases, you see. So this is the formula for psi inverse. We have 9 separate cases to consider. Well, and now it's plug and play, and you have to apply it. And again, as before, the only, at least mildly interesting calculation is to prove condition number 5. And this time, condition number 5 is just a direct calculation. You simply compute. You compute this equation on the left-hand side. You compute, and you compute using the lemma which we proved at the beginning of the lecture. So we must know, for instance, that QV is idempotent, because this is a complicated calculation. It's 1 page long in my lecture notes almost. Yeah. So this calculation was 1 page long, and there is no way we can do it right now. So I'm not going to start it. We will do it next time, and then we will also compute that psi and psi inverse is identity, and psi inverse psi is identity. Okay, so what remains to be done? So A, check these 5 conditions. B, show that psi inverse is identity, and also psi inverse psi is identity. It's straightforward, I repeat, but it's still a calculation. And that's what we will do next time. So next time for sure we'll finish it. And I think unless you have some questions, that's a good time to stop. So any questions for anybody? No. Okay, so thank you so much. Nobody from Zoom? Okay, so I stop recording. Where is this feature? Stop share and